Are you guys ready? Have a nice lunch? Anyway, we're going to continue here. Hopefully, we're going to be on the next hour. We're just going to finish for the day. And then you just can go and do your stuff. So, as you recall, in the morning, we were talking about a way or a mechanistic, empirical way to improve over the psi factor that was available in the design guide procedures to incorporate the roughness due to the expansivity of the solid, right? So we saw that one of the requirements for this project was to be able to be implementable in the already existing design guide for pavement analysis, and therefore they didn't want any desire to do water balance at the surface and get infiltration, evaporation, and get all these CPH analysis and so forth. So we used the Thorway moisture index. The only thing we did was to modify it to, instead of reading annual indexes, we modified this to be monthly, right? So basically, we were able to capture somehow the variability of every year. You can see like probably peaks of high TMI and peaks of low TMI, even if the average value was probably positive for this side, right? In Texas, probably you're going to have a value that is in the order of about plus 10 or something. But you're going to see some of them that there are some months that were very wet, and therefore the TMI is high. And there were some months when the TMI went even to lower than zero, negative something, which means that the evaporation gained over the precipitation at that particular month, all right? So that always gave us that particular variation of the Thorway moisture index, and in particular, more than the variation, the slope, okay? If you have a big variation between the water content, but it takes for that to occur 3 years, right? You probably are going to have some change, and you're going to see that change, but it's not going to do any damage because it's a slope rate, right? But if you have a big change from one point to the next one in a very short period of time, you certainly can do a lot of distresses to your pavement, right? Going up and down. We got a lot of rain, and the pavement goes up, go lower, and the pavement goes down, right? But again, precipitation alone will not give you that value. We tried with precipitation alone before, like to see if that's the only thing that helps. No, you have to, to incorporate also the actual evaporation that you have from the soil. Okay, so this is how we use the Thorway moisture index. It's kind of a practical way to put a superficial value in there that is going to be always, this particular point is kind of your balance point to take water or to leave water. All right. So the second steps was, okay, now we do have a climatic condition, boundary condition imposed, right, at the top. Now we want to figure out how the suction changes with depth, right? The suction changes with depth. And obviously it's going to be suction that are very low and suction that are very high, right? Depending on the moisture content you have here. And therefore, if you just put all those points for 20, 30 years, you're going to find that for a particular site, there's going to be an envelope, right? That you don't go less than that or you don't go more than that, at least theoretically, right? So we found that envelope, the determination of that envelope. I'm going to show you the model for Van and Houston that we use all these constitutive surfaces. Okay, so coming back again to our discussion this morning here, the constitutive surface, if we got something like that for compressible soils, right? For compressible soils, when we have change in void ratio versus either total stress in here or net normal stress or suction. Okay, this one works very well for linear elastic material. So the question is, okay, so expansive soil might not be, right? Because that's something that I told you yesterday. Expansive soil probably behave a little bit more erratic than elastic materials. It doesn't follow elastic. theory. Therefore, how are you going to do that? How are you going to use something like that, a surface like that, including those, fundamental stress state variables? Well, you're going to need from the laboratory to figure out new coefficients for this kind of soil. Okay? Now you're going to have compressibilities that are going to be different for this particular soil types. Okay? So this is how you change the material property. You don't change the constitutive model. So now we were not allowed a final element analysis, right? Like I showed you the work that Yacine did on just trying to figure out the suction profile when the flooring conditions were in there, right? That I'm able to do the whole suction profile, right? Well, we were not allowed to run any modeling on that one. So we use a back calculation of some variables of an equation from Mitchell from 1979, which is a closed form solution of Richard's equation, okay? And then we developed a long-term wet drying suction profile. So let's see at this particular set of stuff. So the first thing we did is, okay, we're gonna adopt a model, right, for volume change. So we adopted the Lytton model when we said, okay, the change in volume is a summation of the change in volume with respect to the hydraulic head, right? The hydraulic heads in here, plus a change in volume due to the load condition, right? So you can put their normal stress in here and the changes in suction in here, right? Or change, and then you have it. And then there is an extra one that we haven't talked much about here, is because it's kind of important if you do have salts on the water, or you got, and this is the osmotic suction, the osmotic gradient, right? You're going to have also some change if you just put a gradient, a concentration gradient in there, that is going to create this also gradient going on. For this particular reason, we consider that the soil chemistry, the water chemistry is going to be kind of the same, and you don't have this big suction or osmotic gradients going on in there, right? Or concentration gradient. So this one was eliminated from the model, so we're going to use the two stress state variables that we saw this morning right there, okay? So this one, volumetric strain, suction compression index, we need a compression index based on the suction, the change in matrix suction, the beam principal stress compression index. If you have a saturated condition, this is your C sub C value, right? The change in normal stress, and that's the osmotic suction compression index, and the change in osmotic suction that we're going to be assuming to be neglected, all right? Yes.
For collapsible soil?
For what?
Collapsible soil?
No. Collapsible soils are different animals, okay? They're totally different. They don't follow this, no.
Coming to your PMI index,
yeah.
That one, can we somehow consider the effect of the pavement?
Let's see how to explain this. Whether you do have an unpaved condition or you have a paved condition, the soil below the pavement is going to tend to an equilibrium condition. It doesn't matter that it takes 3 days, 3 months, or 3 years.
It doesn't depend on the type of pavement.
And it doesn't depend on whether, because if you have a way to get water in there, which is our problem, right? If everything will be paved, then we don't have any problem at all, right? We have no water in. But if we do have a way to get the water in, which is usually about the embankments, right, of your pavement, because you have those shoulders. Sometimes you put some gravel in there, sometimes are open, sometimes are paved, but then you do have the embankment around, right? This soil is going to be tending to get the equilibrium value, right? When you have infiltration rainfall, you get water in below the pavement, and to a point when it starts evaporating, so it's a continuous flux, right? Like we saw on the problem with transient flow. So the answer is, it doesn't matter if you got pavement conditions or not, right? Now, that's a very good question, is because the little model that we're going to see in here, that is the basis for this part of the suction envelopes, were created for areas that they were unpaved, right? So the balance between the environment and the soil was also not only to the lateral flux, but also to a vertical flux, okay? But what we need to understand is that your soil is going to tend to a particular equilibrium value, okay? So you run into that particular equilibrium value. Remember when, and at least on the surface, remember the Pereira model, so we're going to see them in a minute. When you have your suction value versus TMI, right? And we say for a particular soil type, okay? For a particular soil type, if we have this soil in a particular region that corresponds to that TMI, then this soil is going to tend to this equilibrium condition, okay? Equilibrium condition. So let's say this is a granular based material, right? It's a granular based material. And when you compacted that, you compacted it at optimal moisture content, right? Let's say that corresponded to about, if you get to the degree of saturation versus suction, saltwater characteristic curve, the granular based material compacted at about optimal moisture content is about, I always say, between 75 and 85% degree of saturation for all the soils pretty much, right? So you're here, and basically you compacted at that particular suction at compaction condition, all right? So if you get a granular based material with time, and you compacted at that particular moisture content or suction, right? If the soil is located in Arizona, that compacted condition, the moisture content of compaction condition, perhaps is going to tend, the TMI is pretty low, is going to tend to a much higher suction than that, okay? So if we leave everything alone, this soil is going to be trying to go and equilibrate to this equilibrium condition in here, okay? But what happens in the middle road, right, while the soil tends to that particular suction condition, it's going to be some rain going on. So the suction is probably going to go down, right? Oh, I'm sorry. This one is the equilibrium suction will be higher, right? Alrighty, so I'm going to try to erase this, erase it. Happy with this thing. Here we go. Plenty here. So that's your compaction condition, I'm sorry, and because it's Arizona, I said, right? It's going to be tending to a much higher suction value. So the equilibrium condition is going to be here. And it might take, it's a granular base, might take few days to reach, right? If there is no rain and the evaporation, keeps pretty much. But it might happen that during that time, you got a lot of rain in here. So this suction is going to try to go down, right? Like the TMI. And probably some evaporation going on because it was a very hot day, and probably it's going to try to go like that. So meanwhile it reaches this equilibrium condition, you're going to have some bumps in the road. And those bumps are the ones that create the roughness of your pavement, right? So this one is for a soil, another soil, exactly the same soil, that has been compacted at the same value, let's say a subgrade material, which is a clay material, right? For a clay material, perhaps, oh no, it's the same granular based material, but it's going to be in here in Guaha, all right? When that soil, because of the conditions on the environment, are going to tend to an equilibrium suction, which is much lower than that, right? So for Arizona, you're going to see that one, but for Guaha, you're going to see that this guy is going to go down in here until trying to equilibrate right there, okay? So that's the assumptions that we made. Soil will tend to equilibrate to a condition, okay? Because if you have any way to get the water in and out, you will try to do that. All right, so let's continue with our suction profiles, right? So we're going to have a change in suction in here because at the surface we're going to have this condition. We're going to have a wet condition, which is going to lower our suction. Sometimes we're going to have a dry condition and so forth, right? There are going to be points where are extreme to that one, and there are going to be points that are going to be in the middle, right? In the middle. And also they're going to be changing with depth to a point in which, it doesn't matter what happening here, this soil in here is not going to feel it, all right? The famous depth to equilibrium suction, right? So what are the parameters we need for that? We need the change in suction at the surface. We need the minimum suction value or the wet suction, and we're going to have the maximum suction value, the dry suction, and we want a function because we don't have a final element analysis to do what we saw yesterday. So we're going to need this change in suction with depth. All right, change in suction with depth. So in here, for example, at this point or this point or this point, in here is going to be applying two stress state conditions. The suction value that you have, okay, plus the overburden pressure that you have in here that represent your net normal stress, right? If you go down, you're going to have perhaps the same suction values up to a depth, right? But you're going to have a much higher compressibility or movement of the soil due to more overburden pressure, okay? So this envelope represents somehow, that's why it goes down also, represents some of that, okay? But let's talk about the suction envelope here so we don't get too deviation. Oh, I had done some. So again, these are the equilibrium suction envelope parameters that we need. We need the equilibrium value is the one that corresponds to the suction value at which equilibrates with a particular depth, right? There is always a point when the water content is not going to change more because of the environmental properties. And again, we're going to need the depth of equilibrium suction that we discussed yesterday, okay? When basically the change in the dry suction and the wet suction is not going to be greater than, let's say, you can put a number. You're never going to find something that is absolutely no change, right? You're going to have in here some variability associated with that. We put a value of 0.2. All right. And the seasonal suction envelope parameters, would I show you the change in suction, the minimum and the maximum. You're going to say this one is the same, but what I'm talking here is that you're going to have some skewing, right? That's not a beautiful thing like that, a cone, okay? You can be more on the right-hand side or on the left-hand side, depending on the side. Sure.
Here in that equation, sigma F and sigma I, that is a normal stress, overburden stress, sigma F and sigma I. Okay. The equation, second term.
Yeah, this is the change.
How are you differentiating sigma F and sigma I?
Oh, this is the same thing that you do in compressibility, right? The change in volume for your compressible curve, let's say like that, all right? So you're going to need an initial value and a final value, right? And you're going to need this range in order to figure out what is your change in void ratio, right? Okay, so this.
Like if we take an example, like this kind of volume change,
Mhm.
so already we have the pavement stress in the same. Overburden stress doesn't change.
Exactly. The normal stress that you put in there is going to be constant,
Yeah.
totally constant, okay? So what happened is when we give, just give me 1 second, I finish the thing. When we give a practical engineering, like, okay, I'm going to be making a slab on ground for expansive soils. And we go to the laboratory and we do a free swelling test. And we tell, okay, this soil is going to be, the expansivity of that soil is going to be 13%. And then they're going to need to work with that in order to do the slab on grade, right? This is a maximum value. This is a maximum value that we get in the lab. That's a a limit. That's a limit value that we have, okay? Usually what they do is they assume that this value of swelling is going to be the same at the top of the surface or all the way down to 5 meters. And that's a big mistake, right? It's very conservative. The slab, will not fail, obviously, because you're putting a lot of money in there, which shouldn't be, right? Because actually with the overboard and pressure, you're going to see, this is the envelope, your overboard and pressure, because the change is much smaller in here, the compressibility should be smaller right there, okay? So that thing varies all the way down with it. So in that case, this one is not been taken into account yet, okay? So I think I confused you, all right? All right, so this one is only the suction envelope that we observe in the field for that one. So let's go to the next step, because I'm going ahead of myself. Okay, so that's right. So what happening here is that envelope in here basically is independent of the overboard and pressure so far. So we're going to be putting that in a moment, right? The only thing that is a functioning here is that as you go down deep, the environmental conditions are not applying anymore, okay? And that thing can start getting down and down. I'm getting ahead of myself in here and get you confused, okay? All right. So let's keep with the suction envelope, okay? We keep the suction envelope to define the maximum and the minimum values at the surface that the soil will be subjected to due to these weather conditions, okay? So in order to define that, what do you need to define that? Well, again, I told you the depth to equilibrium suction, the equilibrium suction value, the change in suction at the ground surface, and the skewness representation, okay? Because there's some analysis that says, okay, this one is not a nice cubical thing going down. So we use a suction envelope that was postulated by Van and Hirson in 2021. They went over 40 different geotechnical sites studies in San Antonio, Denver, Phoenix, and Mans Park in Arizona. And also they collected literature ranging from all the way from the 70s to 2018 when he graduated, right? And based on that, they basically work out, how this suction varies with time for different soil types and in different regions, wherever they were located, right? So the suction envelope, I just put two things together. I'm sorry about that. All right, so the depth of equilibrium suction, you already saw that, right? The depth to equilibrium suction, they find out despite they put together correlations with soil properties, with, combination of properties and TMI, everything. They found out that the TMI was sufficient and enough to represent the depth of wave, okay? This is, again, when you see all these numbers like this, is empirical, right? It's empirical correlation. And this found this one, but the correlation was actually very good with the data they found. The data from their study is called the surrogate, this study. So they have a lot of data in there, but also data from the literature, okay? So also the equilibrium suction value for so I'm signing in here, right? The equilibrium suction value, okay? So what was the equilibrium value for a particular place? And they also check many different correlations with the data they got, and they found that the best correlation, although the R squared is kind of weak, they found out that the equilibrium suction is going to be a function of TMI, and that was the best thing they were able to get with this data, okay? It's not that bad, actually, for geotechnical engineering, believe me. It's not that bad, okay? This is PF. PF is nothing but the log of suction in centimeters, right? This is a measure of suction.
Did you try doing some soil penetration?
Yes, they did. They did.
Does it give a better?
They didn't. They didn't get any better. Well, if they improve a little bit, they were not worth it trying that. That's exactly right. So they tried different. There's a whole thesis about it, and all the analysis that Van did for that. Jeff Band. And actually, he's a very successful consultant in town. So he has access to many big equipment and many sites, and that's why we were able to get very nice data set for that. What are the limits to the potential suction change? The delta sigma at the top, and for that they also went and checked some data from the literature. The data they found the R squared to be about right, and basically that limits the potential change in the suction at the surface, and it was important because we needed to know how much that's going to change. We don't want to go crazy, like if we have a very bad month, very dry or very wet. So they also found this one to be a function of TMI. And also they found a parameter that accounts for the asymmetrical nature of the envelope. They based their work on the Oveni and Long, which in 2007, they demonstrated that the asymmetric salt suction envelopes are effective. Before 2007, everybody was using a very nice envelope. And some of the good work that is available is from the Australian people and South African people on that, okay? So that was a step forward over the South African people. They incorporated a parameter, which is what a total of suction change in the surface. And basically, that value was a deviation from the equilibrium suction, okay? Over the whole range of suction between the dry and the wet. So it's an R value, which is a percentage from one side, right? From the wet side, on what how much skewing you're gonna get. All right, so we got, these points, the delta sigma, we got the equilibrium suction, we got the depth, and now we need the function. We need the function to go down, all right? For that, they went down to the literature and they found Mitchell 1979, and this has been used a lot by the Texas Department of Transportation. They do have a function in which they have three parameters. Basically, if you find those three parameters, you should be able to get what is the suction at any depth, okay, by knowing what the equilibrium suction is and what is the change in the suction above. And those three parameters were in here, right? The Z, the N, and the alpha. All right. So they went, and because they knew what the suction was at the end, because they took a lot of water contents and they know how much, saltwater characteristic curve. They knew the suction variation with depth and what was the envelope. So they went, and with the data they collected from those 40 sites, they calculated those parameters. Okay, calculated those parameters. They found an equation for that then they could use for any other type of parameters, right? For any type of salts. So that's how they got that one. The weight and the dry limits, the ground surface, the maximum and the minimum suction values were determined with this value, with the skewing value in here from the deviation from the equilibrium suction. And also the dry is going to be the wet plus the delta sigma that they found in there. So with that, they were able to do, and this equation actually, is a very beautiful, a lot of work by many years by Mitchell, in which he ran Richards, it's a Richards equation, okay? And they ran multiple, simulations, and they figured out how to do a closed form solution, okay? So glad we have that, because we didn't, we were not able to run Richards equation on that point. Yeah.
This was based on the field observation or
Richards, no.
Not this.
Oh, the calibration of that equation, yeah, for the field data. Yeah, field data. They did all this soil that they took from those 40 sites, they took it to the laboratory and they did saltwater characteristic curves and all of that. Okay? So what they did is they figured out in the field, we didn't take suction measure, they didn't take suction measure. They went over there and drill, right? They core and they drill and they figured out the moisture content, okay, the moisture content on this place, right? They did that, and they used the same to or to go and check again 3 months later, 6 months later, 1 month later, right? And they did a work about 2 years. They were figuring out how much the water content changes, and you can see the data that they obtained. It was pretty neat. Okay, they obtained, they just did water content determination all the way down, right? They go ahead and took samples, and they figured out how much the moisture content will vary at that particular site.
And they relate with the suction.
Exactly.
From
the SWCC.
This SWCC, did you consider the load effect or it's free?
No, we did consider load effect. The questions are, okay, how we go from the water content that we got in the field to the suction values, right? To figure out these envelopes to be able to calculate those values, right? So in this one, if you use the pressure cell, actually you have the opportunity on the pressure cell. You do your air entry, high air entry stone in there. You just put some load in here. You just put everything down on the valves, and you have a way to get load applied to this one, and put that value on that particular. That was me. Sorry about that. No, okay. So we got this thing, and we were able to figure out saltwater characteristics corrected by volume change due to the different overburden.
I'm more interested to see the variations with under the overburden stress. How that is
Interest on the variable.
The suction variations, suction and volume.
These guys,
Does it get influenced by the overburden stress?
the water content, no, supposedly not, right? The water content is not, but the suctions do.
Because whenever there is a change in the suction value, saturations, under the load is slightly eventually
Yeah.
this will impact the
Yeah, but okay, so we're talking about the saltwater characteristic, right? And you said, okay, we got water content in here, and we're going to get suction values right here, right?
because it's an expansive soil.
Mm-hmm.
Whenever there's a change, you have some loading.
Exactly.
Change.
So you took that sample that was very expansive, actually. You took it out from here. You took it out from here. You took it to the laboratory, right? And basically, what you have to do is you need to consolidate or just load it again to the overburden pressure that it was experiencing in the field, right? So basically, you return the stress history to that point.
My point is when you are trying to get all the suction profile there, suction you are going deeper, overburden stress is changing.
Yes.
Right? So I just wanted to know from the lab when you are going to the suction, field is at the moisture content.
Yes. So we measured the moisture content. We took it to the laboratory to the SWCC on that sample that we took from there. So in order to do that, we loaded to the overburden pressure that we got at that point. You load it to that overburden pressure, and you eliminate any expansivity that you get due to that unloading that you had to do. So you load it again to this point, and then after that, you do the equilibrium analysis.
The number of SWCC, different overburden.
Yeah, so you took a sample in here, then you took a sample in here, and you do the set. You vary this normal stress here.
Number of SWCC.
No, it's one. It's one, but corrected for volume change. You see, any value, it could be higher, low water content, whatever you get in here, but the value is already corrected by volume change. Okay, at least it incorporates, it actually is now independent of the overburden pressure because you put it in there, right? And then, therefore, you are going to be having this results. Great questions. So that's how they were calculating those values, and they were able to use the Mitchell equation for that. All right. They got at the ground surface, they have the minimum and the maximum values were determined with the values they found based on TMI. Then they use the boundary condition for the suction value at each depth, because this is the question that you have, suction at any depth for the wet, no suction, the wet envelope and the right end and the dry envelope. They use the equations in there, and it should be in here somehow the Z value, right? The depth, right here, right? Right here, the depth value. All right. So you do have now the suction with depth. So that's how we create those envelopes. Okay. Now the next set of steps, it was the generation of the changes every month. The changes every month. So we know the big picture, what's going to happen with the years on the dry, on the wet side, but now we need all this, and for that we needed to figure out how to calculate that time varying suction, right? The time varying suction. The first thing we did was the deterministic approach, right? We only have data from weather station, past weather station data. So we were not forecasting anything on the weather conditions. We have only the data from the past. So that thing you can use for case studies, forensic analysis, calibration efforts, or so forth. Okay. The stochastic analysis, on the other hand, when we have randomly generated monthly TMI, you got to estimate that based on historic data. Then we are able to do an associated variability with this particular data set, right? And this case, this analysis we use for design future pavement structures, okay? Because we do have determined an stochastic analysis for that. I'm gonna show you how we did that. So the time varying suction at the surface, you've seen this model before. Actually, you use it in part of your exam for tomorrow. It's based on the work by Pereira. The two models were available as you check the granular-based material and the sub-base or sub-grade material for coarse-grained soils. I already talked about how we obtain these models, visiting also a lot of sites in the United States for this. And basically, this one is kind of the equilibrium suction at the surface, right? Or near the surface, very near the surface. We didn't go deep. But we included, actually we did went deep. But there were two things that we had in here. We were deep on this analysis, but also the Van group also went deep, okay? And they figured out the suction at equilibrium. So what we did is we used Pereira models to estimate the suction at equilibrium at the surface, okay, how that varies. Then we use the model to go to the suction at equilibrium at depth using the Van model that we got in there, the depth at this. So that's how we combine the two models or the two informations available. So you know how to use this one, depends. Anybody has any question on the homework assignment for last night? All right, while we're here. All right, so this is what we got, an equilibrium value for this. So we do have the Torway moisture index, and when you have the Torway moisture index and you apply those models, you were able to get now the estimated soil suction at the ground surface, okay? It's just applying those models, right? So from the Torway moisture index, which is this guy, we were able to get now the changes in the suction due to those changes in the environmental conditions, okay? Now, there were some adjustments that we have to do at the surface because remember that the Van found an envelope, and some of the data that we did with the Pereira went out of the envelope, right? Because we did it for different soil types, different stuff. So basically we accommodated the changes that we got for the Pereira within the envelope that the latest group of researchers have done, okay? And this adjustment of the suction variation was, using the Van. It's almost the same, but it was a little bit of tweaking there that we did for that one. It's just a small equation here to be able to see that we were into the envelope, within the envelope. Now, the problem in here is feeding the surface suction data, because now you do have this guy. Okay, you got this guy all over the place, suction going up and down, right? If we have only temperature, that would be a very nice sinusoidal stuff, right? You look at the temperature, it usually goes up and down, very sinusoidal depending on the climate condition that you're going to have and the seasonal variation. But when you do have TMI, you're incorporating the rainfall in there, which is the tough thing to do. And now if you want to put it in a model that is a continuous model, you're going to be putting all this crazy data into a function, right? So sinusoidal or periodic suction is not going to work. It's not going to work at all. So we jump into the Fourier series, right? And and we start getting into 1 second order of magnitude, first order Fourier fit will give us, this value here. The 8 order, we give you a little bit more the jump. We were trying to catch up the jumps, right? The peak points that will cause the problems in the road, right? We don't want it to smooth the suction. We want it to be as precise as possible as the data that we found in that one. And then adjusted, so basically we went and 1 to 8 orders of magnitude, and then we were able to do in MATLAB a code that will adjust the end value of the Fourier series to the one that was the better fit for that. Okay, so that's another work that we do. We improve the 8 order of magnitude. Did we lose them? Okay, so let's give it 2 minutes. Oh, they're there? Okay. So we did a lot of work, there was a lot of discussions about that until finally we were able to optimize that order, Fourier order, by creating an algorithm that optimized that thing. So sometimes it ended up with a Fourier number of 32, sometimes with a Fourier number of 18 or something like that, okay? But in that way, we just save time in not running this one to a very high Fourier number, which is going to create a lot of data management. And we did a very good job. Like, we started with a minimum order with the red pointing here. But if you see the blue lines and the natural order of magnitude and the little points we got, okay, this is pretty good. Now we are able to catch every single thing with just an equation, all right? So we did that to figure out what was the variation of the suction at the surface. Okay. Then we use the Mitchell equation to model the suction profile for every time step down. And again, this is the equation. This is the equation for that salt suction or forward pressure in here. So you see the first month we got this particular location, and then for the second month, that changed, and then we use the equation, and that thing goes into like that, and we did that for 12 months, and with that for many years that you want to do. Okay, so that will run 10 years, and that goes up and down. You go to the largest but now we were able to capture all of these changes in the climate by changes in the suction envelopes profile that we got. Okay. Then we did adjustments, and here is what your Danish answer is. Okay. We accommodated. First of all, remember expansive soils are unsaturated soils. Usually, of course, in areas when you have groundwater table at a greater depth. Okay. Obviously, if you have groundwater table that are shallow, you need to cut down the suction to a 0 value at that particular point, or you need to merge the capillary rise with the envelope in here. This is a word for you guys, okay? I don't know, we're gonna do that, but this is something that we have for next, right? Future research recommendations, right? What we also we have nearby vegetation that creates extra suction values, okay? So probably those envelopes will change because you have very aggressive trees around that is going to take a lot of water, right? Or some other stuff like that. So there are many things that we can do with this model. Some of these roads that have a lot of expansive soil, they put moisture barriers, right? And they're vertical. So now this is going to delay, right? This and the envelope might be narrow in that case. And also we need to adjust the function because of the net normal stress that we were talking, the overburden pressure, right? And that's how we incorporate the second stress state variable. So the overburden effect is fully considered, and what happens is, if you have no overburden, this is your free swell that you're going to have in there. But as you have overburden, that thing is going to start going, lowering here and lowering here. And now the swelling strain is going to be lower and lower, right? Because and as a matter of fact, if you go to a certain depth, that's another one of the nice discussions this morning, this kind of model will tell you that that soil that used to be expansive above can collapse when you are down. And we've seen collapsible soil, collapsing soils or compressible soils or compressing soils that are expansive in the laboratory as well. Okay, so that happens in here. So this one is for example, the lines how you adjusted by overburden pressure in the corners, right, to the corner of the road. But what happened in the center is different, right, because the main exposure of the road is going to be at the shoulders, right. In the middle, it's going to be some, but it's going to delay more, okay? And once you get the infiltration in here, when it started evaporating, the flux goes down, and probably it's going to be very small change in the middle. Nevertheless, that's why we got the cracking forming because of the flapping. And basically, the change in the expansivity is much less under the center of the pavement, okay? And this is a model that was also put together by Litton and his group of researchers back in 2012, I think. And this one basically created an equation that if you knew how much was in here, you were doing, how much, expansivity you will be allowed at the center of the roads. Yeah, so I'm just talking about that rigid foundation, and I'm thinking about that, but we'll include that later on. Okay. So some validation studies were done. We started with that. These are measured data. We see that they were mostly on the dry side, and we were just not being very good. We're being okay for the deeper section, but not on this side. So, they start adjusting a little bit more until we were able to get this on the, at least looking at in here. And what I'm looking in here is, okay, what happened this particular day, right? This particular day. This is my model, and these are the measurements that we got in the lab, in the field, right? So at least, gets the right tendency to go down at that direction, okay? So it's obviously a lot of variability associated with that, but we were able at least to get into the ballpark of those predictions. Okay. Now we got the suction envelope, we got the suction profile, we got the changing suctions with time. Now we need to translate that suction into volume change, right? Which is the important part of it. So how to do that? So the first thing, it was, like I said, we need a compressibility index, right? Anything that you do, whether overburden, whether net normal stress, whether effective stress, for suction, you're going to need a compressibility value right there, okay? So there is a very famous work done again by Covart and Litton, McKean, 1989. This is Colorado, U.S. Geological Survey. And they did that one for, again, post-tension slabs on expansive soils. And basically, there are a set of graphs that relate the suction, the strain, or the suction to volumetric, the total suction to volumetric strain. And basically, it is an empirical set of graphs that takes into account the soil properties, right? If you got more PI, passing 200% clay, you use all of these parameters as we saw yesterday in our lecture for problem soils, that you can actually estimate some volumetric strain going on in there, all right? So that work is available and is there and is being used. That this is what is being used for the last, 40 years, 19 to 25, 35 years, 40 years in the United States, mostly in Texas, where we got, in Colorado, we got a lot of expansive soils. And also, one of our students, as part of this study, Mohammed Mosawi, he basically took the soil water characteristic curve, right? And he started measuring the change in volume just to the applied suction, okay? So we put in that cell, we put an LVDTs, right? And we start changing the suction, and measuring the volume change for all those expansive soils that we had in-house from the previous study from Van and Houston, okay? So we did that, and he was able to find, the change in void ratio versus suction as you go that. And they translated this one into the strains versus suction. And basically, they were able to find, at least a compression index, but at least, a relationship between the change in void ratio and the change in suction and the change in normal stress, okay? And he added the WPI, and I don't have the R squaring here, but it wasn't bad, it was good, okay, with the data we got. So we got passing 200, PI, and the two stress state variables in here, right? Okay. So it's a combined compression index, right? That takes into account the two of them, because we are not using the constitutive surface on the model. Okay. So we calculate the volumetric strain because we got now the compression index from Bob Litton, but again, we do have this one. We haven't implemented this one in the model, and with that, this one, which is our mean principal stress compression index, which is the one that you know, right? C sub C over 1 plus E naught. And the other one we neglected. All right. Calibration was done for a very small amount of material. This one finished in about 2 or 3 years ago. And what is the problem? The problem is we don't have measurements of deflections pretty frequently on these soils, all right, on this particular. So we went for data from the long-term pavement performance, which is a big database of data that we got in the United States, and figured out deflection information for places when we know that the soil is expansive, okay? And some of that was caused by expansivity, right? So we went for the very corner, that it was the one that it was just flapping out, and sure enough, we start adjusting to some of the values that we found, that we calibrated. So we developed statistical correlations of measured versus predicted. Not very good, like you say, an R squared of 0.61 is, okay, this is for asphalt pavements. We used 58 calibration points for that, 41 for the AC sections, and 17 sections for the pavement, rigid pavements, right? And we were able to get a much better correlation with this. And obviously, the recalibration is in progress because we need more and more data for doing that, right? These are kind of poor correlations, but the framework is there. So in that way, we were able to figure out a volumetric strain for a particular region and for a particular type of soil. Now, what if we need to predict what's going to happen in the road, right? What if we need to incorporate this one into the design procedure? The road hasn't been built, right? And we need to give out a good estimate of what we're going to be expecting if you do that one on this expansive soil. So this one is when the stochastic solution comes into play. And stochastic means, that will allow you all this variability associated with the climate and material properties that in turn is going to behave as the variability associated in your suction parameters, right? Your suction envelopes in here. And not only on the suction envelope, but also on the equilibrium suction and so forth. So the variance associated with the volume change response is what we consider to be representative of the roughness experienced by the pavement at that particular point, okay? Because it's the change, right, that creates that variability, okay? Again, we use Monte Carlo, which is simulation. When you do a lot of simulation for that, we start with Monte Carlo. But again, when you deal with climate, you need to be very careful with Monte Carlo simulations. Why? Because stochastically forecasting of time series is not a very good idea for that. Why? Because the climate that we had today, Friday, is a function of what happened yesterday. And it's a function of what happened last week, okay? So the climate today is a function and dependency on the 2 or 3 days before, or the 2 or 3 months before, how the climate is going. So you just can randomly generate a number for TMI, right? Or for infiltration, for temperature. So this is what happened when you put Monte Carlo simulation in there. You get the average value there, but you are all over the place. When you consider time series data, there is a model that is called Markov chain random walk, okay? Basically, it takes into account for this particular simulation what happened yesterday. So we can take 2 or 3 days before, and if you see now the estimation of the climate is going to be a little bit more, centered, and it's going to be more adequate for and that's what environmental or weather people do, right? They just do forecasting with that kind of model. So that's important, and that improve a lot our predictions on that and what we will get. So we use that, and again, you can predict TMI before if you have the data, and there is a point when you want to forecast, okay? So you start just, making that prediction on that. We try different parameters, like, for example, the changes in TMI. For the temperature, it was very good. Temperature is very easy to predict changes in a long run, right? Not what's going to happen tomorrow, but in a long run, you're going to be able to predict very nicely for the temperatures. For the TMI, was a little bit more rough, but if you can see just every one of those simulations, we're going around, right? What we will expect. We have no idea what is there, but so you just create many of those simulations until you get values. Right. So how we incorporated this model that now we do have a value for the volume change, but also we were able to stochastically estimate everything that I've been showing right now, right? The temperature, the infiltration, then the TMI, right? And now you got variability associated with that, all the way to the suction profiles, soil properties. Even we included variability for the soil properties, okay? Because even if you go and I tell you, 3 of you, please measure this PI of the soil, you're going to give me 3 different numbers, right? So even associated with the laboratory testing, you're going to have some variability associated with that, okay? So we incorporated all this variability into this stochastic model and basically use the variance and the standard deviation associated with the volume change response, okay, that will serve as a surrogate and replacement of that famous psi factor that it was there before. Okay. I didn't bring this in here, but this work was done in conjunction with Case Western Reserve University, and they did a model, and this model was, that was easy because the temperature model was already created in the guide, and they did a frost heave analysis, okay? So we were able to also create values when you do have frost heave soils. We were able to create a psi factor for those values, okay? So this one is for the ones that we created. Again, we just trying to change this guy in here and just by the values that we're getting. And basically, that's the same, you know, like we can do it in overlays, the flexible payment with overlays, rigid payments, concrete payments, all of them have the psi factor, okay? So we were able to modify that one. And even though if we don't include a slab theory for rigid payments in there, we were able to empirically incorporate the rigidity of the payment by just working with the right equation that they have for payment analysis, all right? The variance found to be provided the best fit. We tried standard deviation, variance of the slope, you know, many factors we use. The sum of the square residuals dropped more than 75%. The sum of the square errors also more than 50%. And the R squared increased from 53 to 78%. So we did have many, until we found out the best combination. We used 171 data points, IRI measurements in the lab, in the field, real IRI measurements on places where expansive soil. And the IRI, they measure in the wheel paths, but they also measure values close sometimes, you know, that they do different ways. But we did that. We used the R square, the variance, and the prediction IRI with the measured IRI was very good when we incorporated the variance associated with that result. So if you see, this is another word, right? It's not modeling, it's not very fundamental, but it is based on more mechanistic analysis than just to put 3 values in there for PI passing 200 and precipitation on that, okay? So these models are now being incorporated into the design guide, right? And we got models for soils that are also frost heave. And now, you know, there one student in Case Western that are trying to figure out soil that are frost heave and expansive at the same time. You see, we just combine it. I don't know. That's how that's going to work. Empirical regression analysis model performance. This is we compare the new IRI model for AC payments with, you know, the same equation that we got before. And we got this is the site monitoring versus the model. And this one compared, this one is an R square of 0.63, improved, you know, the variability associated from 54 to 63. So at least it improved. I'm telling you, this is a very good prediction for IRI. This is very variable that we got here. So this is what I got for you today. Okay, what time it is? 3:36. Do you guys have any question with this? At least the way we did stuff. Rahul?
When field deformation measurements were done for volume change, parallelly there would be traffic going on, right? So there would be that primary, it is based on the age of the pavement, it would be either in the stage of primary or the secondary compaction. So
Okay.
so the data is coupled with both traffic movement and the soil character.
And you're talking about the data we use for the calibration
Yeah.
of the information part of it? Yeah. So if you check a payment or the LTPP, what you're going to have in here is, that's your payment, right? And you're going to have deflection measurements at the crest, deflection measurement on the outside wheel path, and inside wheel path, you know more than me that. And they also have one very close to the shoulder when there is no traffic. Okay, so the ones that we use were those guys in here. Okay, which will at least avoid, you know, the deformation associated with the rutting condition that you're seeing. Good questions. They have like 5 or 6 measurements in there, so we were carefully with that. It's very difficult to find out, you know, it's also a lot of money to be able to estimate and to put strain gauges in there to figure out how that soil will change. No, they don't do that. Any other good questions? Bad questions? Questions? Why, guys? All right, tomorrow we're going to come here a little bit also for a very practical applications of geosynthetics. Okay, we're going to be looking at that, and I guess you're going to have your valedictorian ceremony on that. Yeah.
Really mentioned about recovery time.
The recovery time. For recovery time after a flooding condition, moisture changes. Okay.
Do that, like, have you worked on that to estimate the recovery time post inundation or flooding event?
Okay. So I don't have any. Yeah, I do have it here. Well, what I showed you last time was a table, and I think I can find it in here really quickly. That was the example we had in here, right? Here we go. So if you check in here what, we're at this stage, this is in progress right now. But what we have in here are the different soil types and the changes in resilient modulus or moisture content or recovery, right? With time. And we run this one for about 100 days. We can have run this one for a year, something like that, okay? But a road will never allow us to open in a year, even if I tell them that thing doesn't recover, right? Because they need to open the road immediately. So basically what we're going to be using this kind of data that we're getting is to inform the state agency how much loss in the estimate you have, right? And obviously we did, we did a little bit more at the beginning, like the first 1 or 2 weeks, right? Because this is, and we find out that, for example, for the first 2 weeks or the first week, okay, depending on the soil type, you either lost 11%, 17%, 13%, but some of those soils you can go all the way to 50 or 60% reduction in a week, right? And it could be that is progressing towards that. This one is keep going. It's still being reduced after 50 days, okay? So obviously, I'm not going to suggest them to open that road if you do have this kind of soil flooding, okay? But what's happening here is they need to make an estimation of how much is the 10% and how much will that affect the traffic log. We can do that with a couple of methods, all right? The old Ashton 93 method has an equation in there when they said, okay, this is the number of repetitions that my road is going to maintain if I got this resilient modulus, if I got these soil properties, and so forth, okay? If I change the resilient modulus by reducing 10%, they immediately will know how much number of repetitions they're going to lose on the road, okay? This is one way of checking. Another thing is how much capacity you're going to be losing on that, and they can figure out how much thickness they're going to need to put extra if they want to have. So they have ways of knowing, okay, how to incorporate that reduction into the real capacity loss of the paint at this point, okay? And Ashton 93 is an old method, but a lot of people use that one. Or you can run, a design guide, a new design guide, and basically figure out how much routing you're going to get if you just lose this amount of, if you reduce resilient modulus, right, to the maximum reduction value that you see here, and figure out how much time on that. This is for the loss of capacity. For the opening time, you basically, for the recovery time, you're going to tell them, okay, look at this. This one goes to 53%. So I'm very sure by the 5th day, you lost only 20%. So probably you're going to be able to start getting the small trucks or something like that. If you have a low volume road, probably that's not going to be a nice thing to do. But if you have a high volume road that they're looking at the number of, big trucks, that goes to that one, probably they're going to be able to get cars around that with 20% reduction with no problem, okay? So this is something that they, in their experience, they will know where to open the road for that. But
Basic,
we give them a tool.
okay. Basically, like, do you assume it to be elastic nature? Like, whenever there is a loss,
What do you? Sorry.
that modulus behavior, do you take it as elastic response? Like,
Yes,
once,
this is elastic.
Elastic
This
only.
is a resilient modulus.
okay.
This
Like,
is a
when we
modulus.
talk about loss of 50%, 60%, so in that case,
Exactly, it recovers.
okay.
You will recover exactly. So, as a matter of fact, the equation is an elastic model equation. Yeah. So that's a good question. I need to check that out
Okay.
because then you have to check into what kind of nonlinear relationship we got between the modulus and the water content, right?
Right.
And these are not,
Because
they are nonlinear.
the strain level is very high, 60%.
60%.
The loss is 60%.
Right. So what you're saying is, no, but again, the resilient modulus of the soil is the capacity of the soil to withstand that number of repetitions, right? And
Yeah.
this is the recovery strength that they get. All right. Now, in order to do rutting is already when you do have failure, right? When you have a shear failure. You basically do a test with a deviated state until you fail the soil, and you count the number of repetitions that you need to fail that soil.
Okay.
And that becomes into the elastoplastic behavior, right? But this one is the resilient modulus of the soil, the soil that, and obviously you just get some repetitions that are creating some ruts, but not a failure, a total rut failure. This one are repetitions that the pavement will be able to withstand, the soil will be able to withstand.
Okay, ma'am. Thank you.
Yeah, but this is a good question because actually what you got in here is that change in environmental condition as a function of degree of saturation. Okay, and this one is kind of a non-linear, right? Non-linear function, right? So if you have an A6 soil, which is a WPI probably about 20 in here, right? So if you went from a value of optimum condition and the reduction was because you get all the way to here very saturated, right? You got very saturated. You need to dry it again when you're gonna go in here. But I guess it will recover. The analysis is that resilient modulus mean, elastic modulus. Good question. Make me think about that. Any other questions? Alrighty. So that's all I have for you today. So I guess I'll see you tomorrow, right? We're gonna be finalizing here with the lectures.
Excuse me, Pope.
Yes. Any questions right there?
On this slide. So actually, this is from the lecture number 9. Lecture number 8 from today's class. Could you please explain the slide number 22, which was related to extended Bohr Coulomb failure in weather?
All right. So today's lecture.
Lecture number 8, slide 22.
Therefore,
Sorry.
Yeah, I'm looking at this one. The shear strength.
Exactly. Extended Bohr Coulomb failure in the shear stress versus the net normal stress in the he had. So you were explaining something about the effect of suction when you were calculating 5B.
Oh, yeah, that was the discussion this morning.
Yeah, I can show you the place. We just a moment.
What slide did you mean?
This slide number. Can you see?
Let me check. Okay. This is when we get now, this one is the saturated condition, and then we get into the extended Mohr Coulomb failure envelope for unsaturated salts, right?
Correct.
Here we go. All right, so what I was telling you here is that if we want to extend the Moore-Coulomb criteria to account for the unsaturated soil condition is that if you just check this graph in here, the first plane that you see at front is going to be your net normal stress versus shear stress at zero suction. Zero suction means this plane is the saturated plane, right? Is the saturated plane. Are you agree? Do you agree with me? Do you understand that?
Yes, yes.
So all these more circles that you got in there represent, get a failure surface that is for the suction equals zero condition, right? Suction equals zero condition. Now, if you start increasing your suction, basically what happens is that the more circle is going to be bigger. At the same confining pressure, you're going to have that your suction, the more circle is going to be bigger, and therefore your shear strength is going to be higher. And how much higher it is? Well, whatever contribution of the suction to that. That for this particular model, Fred Land uses a linear increase in the effect of suction over shear strength by considering the tangent phi being here multiplied by the suction value. So as you increase your suction, your failure envelope becomes pretty much, if you have the saturated condition here, and if you just use one value for phi b, it's going to become parallel to that one, and it's going to be increasing that amount. This thing in here is going to be the contribution of the pore air minus pore water pressure times tangent phi b, right?
Correct.
Okay, or the tangent b. So, is that clear now, or do you have an extra question about that?
No, this makes things clear.
Okay.
But like when we have to include that thing, in case for the case of repeated load, right? So in that case, suppose we are going to use for this constitutive model, which varies linearly with the depth. So in that case, how we are going to implement this angular.
Okay. Repeated loading. This is for a static loading conditions, right? This is the theory of shear strength for static loading conditions when you applied a confining pressure and when you applied vertical stress or a loading stress. So how the shear strength applied to repetitive loading, right? Repetitive loading conditions. There are more theories that relate to that one, but in payments analysis and design, there are a different model. They don't use Moore-Coulomb models. They use, and I don't have the models in here, that when you do have a lot of repetition, and we were just discussing that, a lot of repetitions as a function of your deviator stress, and that thing is going to be increasing until it fails. Okay? The model I don't remember is like the number of repetition is equal to deviator, over the, so to a particular value here, or I don't know, a B or something like that. I don't remember the number, the model that they use for that. And basically that represents the number of repetitions that you do have in order to fail to cause rotting in the soil. That's called rotting or permanent deformation, right? But I'm not familiar with that. This is very payment related stuff and I don't know. But definitely they use the deviator stress. They use, I guess the Coulomb failure is going to happen, right? It's just going to be something like that until it fails, right? So the thing is, now instead of loading it to find out resilient modulus, when you do that, the loading to be close, not too close to failure, Now they're going to be loading it until they get failure, right? And I guess the criteria will work and will apply, but they don't use that when they use an equation related to the number of repetitions to failure. But I don't have the equation here. I must be, I don't know. Do you guys any payment guy in here that tell me that? I don't remember exactly the equation, but there are some models, actually the little model for permanent deformation for soil. And it works also for confining pressure for, consolidation. Do you have that, Rahul? We're not here a payment expert, so I'm going to give it.
So the first part takes into power law,
It's a power law.
and then the second part where it is exponential, the secondary compaction where the deformation is very high.
Okay.
So it takes exponential.
So you got something like that and then go like
Yeah.
that. Okay, like a flow number for the asphalt or something.
Flow number. So the first section is the power law. The first part of the equation takes power law form,
Okay,
and then the second part.
like of a hardening situation.
Yeah.
Here we go. Yeah, I don't know. I don't have the model, but it's a model. Thank you, Rahul. Yeah.
Thanks.
Those are permanent deformation models, like they're available and they use that one. And again, is with the number of repetitions, right? That you're gonna have in a particular amount of time. That's how you fail the soil for that. I don't know much about that one. Good questions. Any other questions that you may have in here? All right, so you need to study for the exam. Okay, you need to study for the exam. Any other questions? All right. All right, guys. So class is dismissed. Thank you very much for your attention. See you then tomorrow.